All right. Hey everyone. My name is Shreya and this is Kimberly. Are we good to start?
Yeah.
Awesome. Okay. Hello everyone. My name is Shreya. This is Kimberly and we're working with the team with Smriti, Rishika, and Sane as well. And our team project is called Sandeep because we're trying to send an deep sea ocean sediment sampler down to the bottom to the deep sea or a sand sampler, and the word Sandeep in Sanskrit is like means light, so we're trying to shed light on the bottom of the sea.
That's the first thing.
Yeah, I think so.
It's the name.
Yeah. Sane, are you able to?
Yeah. Okay. Yeah. So the issue is with the deep sea mining. As we know, the solution that have been used, they are toxic to the marine ecosystem. And also, if there have been oil spills or any of the things which decreases the dissolved oxygen level. So our main motive is to have a sampler which is frugal and which is non-toxic, and also, it is not hazardous to the biome. So the next slide. Okay. So our main goal of Sandeep is to eliminate the deep sea biome, and we have a frugalized method of extracting the deep sea biome through a lot of the things that we'll discuss. And it is frugal, it is sustainable, and we'll go with this. Next. Okay, so current updates about this, people and researchers have been used extraction method for manganese, but there have been some of the demerits, as in it changes the pH, it increases the marine pollution. Also, the current update is that is being used for the drilling is the George resolution, and this George resolution retiring, it can go deep into the deep sea, about 3.6 million feet. So we have a solution that which can change, and we hope so that we can extract the biome easily. Next. Sam.
Wendy, are you on?
Here.
Should we just go for it?
Sure.
Okay, so I think a couple of our team members might not be online yet. They were having some issues with getting locked out of their housing. So we'll just go ahead and talk about it instead. But essentially about 3/4 of our planet is covered by the ocean. And while the average depth of the ocean is about 3.7 kilometers deep, the deepest parts go to 11 kilometers deep. So that's a very wide range, meaning that we simply don't really know what's going on that deep. We have no insights at that depth. And while it's approximated that we have over 2 million species in the ocean, we have less than 200,000 that are currently well known to us, meaning that if there are any issues with deep sea mining that are impacting these species, first of all, we don't know what they are. And second of all, we don't know how many we're impacting. So it's definitely an issue that we need to figure out in order to be able to sustain that biodiversity.
Okay, so some of the functional requirements for our solution, mainly we want it to be revolve around being an educational solution. So we want to be bringing light to the deep sea where not many people are able to like go or see. So we want to be able to share that with the global community. And so our solution is a deep sea sediment sampler that is passive, meaning that there's no electronics involved in it. It's very easy to use, very lightweight, and so someone could just toss it off the boat, it'll go down and come back up. All they have to do is like grab it once it surfaces again, and no work will have to be done as it's collecting the sample. In addition, deep, we talked about how deep the ocean goes. Our target depth right now is around 4 kilometers, meaning like that average depth of the ocean. But as we'll talk about later, with our mechanism that right now it could be scaled to go practically as long as our timer allows, and as dense as we can get it to sink. And then in addition, another requirement was that we want to do molecular monitoring. So we want to be able to detect species of all sizes up to the micro scale. And using a molecular method with like sequencing will allow us to do that for species both that we know and that we're still figuring out, which is very exciting. And clearly, we would like to be very frugal with this. We want it to be accessible for a global community. We want it to be scalable, adaptable. And we really kept this in mind when we were trying to work with materials. We'll go further into that, but we had fun with that for sure.
Yeah, and so kind of as a reiteration of the main facets of a project that we want to go into. We want our device to be distributable to a wide variety of users. So for example, anyone who goes out into the ocean for several hours a day, just as their normal, for their normal day-to-day activities. For example, people who run large vessels, people who are fishermen who are out all day. So again, reiterating that in order for this to be accessible to them, it has to be frugal, it has to be very lightweight and easily retrievable. And so once a broad audience has this, they have to be able to simply drop it into the ocean and then it's hands off from there. The device sinks. Once it reaches the bottom, it's able to collect sediment and then that triggers a mechanism where it comes back up and it's easily retrievable. And so for that, we have the egg timer prototype, which is the way that we fashioned this device takes inspiration from fish eggs, which are able to rise to the surface after being laid somewhere deeper in the ocean. And so we'll go into that a little bit.
Yeah, so this is a general overview of the design iterations that we went through for the egg timer prototype. The main components here were we needed to have a buoyancy mechanism, a weight mechanism, and we chose for our trigger to be time-based. That way we can control what depth we want to go to by calculating how long it would take to sink to that depth. And we'll go over all of these in detail now.
Yeah, okay. So our first challenge was to determine how we're going to get density, or how we're going to get something to sink and then also to rise. So some sort of buoyancy mechanism. And originally we started out thinking about chemical rising mechanisms, meaning that somewhere along the way after the device is sunk, we can produce a gas through some trigger by mixing different chemical reagents together that causes it to rise because of how the low density is of different gases. But then a couple of issues arose with that, mainly pressure based. One is that a lot of these gases are completely liquefied at these pressures and temperatures, meaning that we don't actually know how well they'd be able to rise, and also if we'd have any issues with them exploding, because after they come up to the surface, because of the huge difference in pressure between 0 and 4,000 plus kilometers being underwater, like that gas would have expanded a lot and potentially caused damage to our sample or even lost our sample. So we shifted from that, but kept the same idea of density and instead switched to liquid buoyancy mechanisms. So anything that is less dense than seawater will rise, and anything that's more dense will sink. So we decided to test this idea out with coupling these two ping pong balls. The top one has a less dense solution of 50% oil, 50% pure water, and the bottom ping pong ball is 4 times as salty as the outer solution, which we made like that water tank to be about the same salt concentration as ocean water. And so when we coupled them together, depending on the concentration we chose of the water to oil ratio or the salt water concentration, they either rose or sunk, meaning that we'd be able to tune that concentration to get rising and sinking. So if we wanted something to sink, we could make that salt concentration very high. And then somehow if we were able to disperse that seawater or that salt water once it got to the bottom of the ocean, now the only thing tethered to the device would be the oil or the pure water, meaning that it would rise. And the way that we wanted to tackle this was through a host timer. Shout out to some Home Depot staff that also happens to work at Stanford for recommending this to us. So basically what this timer does is that you attach it to a hose faucet. And so once you turn the dial, this dial right here, once you turn this on the timer, water will be able to flow out. And then once the timer hits 0, there's a plug-in here that blocks the water from exiting. And so the water turns off, even if you leave the spout on.
Okay, so as Trey described, that's how the timer starts when we got it. But in order for us to couple it with our buoyancy mechanism, we wanted to reverse this timer mechanism, thus that when it sinks to the bottom, it's going to release all the sea, or when our timer goes off, it releases all the seawater. And when it's on, that's like when our device is sinking. And so you can set that time for as long as the depth that you want to go to. This is how the timer, when we got it from Home Depot, like $10. And we it's pretty concealed. We just know that like people plug it in to the hose, they set a timer, water will come through, and then when it turns off, it's like meant to like save water, so the water will stop. But our first step was really just like understanding how this thing works, and figuring out how we would want to reverse it. So as you can see here, we pretty much demolished this timer. Yeah, this is the state of it now. It involved sawing some pieces off and moving them. Also it involved like opening up to look at how the clock mechanism worked. And really importantly for us was understanding right here how this trigger works. It's based on spring tension when the bottom is on. And this controls, if you can see in like the hole right there, through that circle, there's like, if it can drop down, that's what connects to the other side, and that's how water flows all the way through. So when there's something that caps below that circle right there, water won't be able to flow all the way through. And that's the state that we want it to be as we're sinking. But if we can use the spring force to pop that piece up, which like we added that little circle thing, which is right here now. But if we can pop this piece up to uncover that circle at the depth that we want, then water will be able to like flow straight through. So hopefully our dense salt water will be able to come out, circulate with ocean water. It'll lower the density, and then it'll rise back up given the oil in the top compartment. So that's what we've been working a lot on this. We'll have some examples. We left it overnight epoxying, and somehow our piece has widened. But we have figured out how to reassemble this whole timer in reverse mechanism, which we'll play some videos on.
Yeah.
And a very important component of that was Ross just walked by. He donated the spring for us. It's a stronger spring that would enable this piece to slide up further to actually allow water to get through. So the spring was a main breakthrough, as well as figuring out we use like, actually we kind of made our own O-ring.
Yeah, we took inspiration from a syringe and how like syringes work. So because we wanted that pump to be able to move up and down really easily with the spring, but we didn't want any water to flow through. So something like a syringe is able to move really easily, and yet that piece of rubber is able to fully block any liquid from pouring out in either way. So that's what we were trying to model with this.
Yeah, and we also flipped like the way water runs through the device. Like usually the side that the hose comes out, we found it was easier to work the other way. So we kind of just flipped this whole device.
Yeah. All right. And so once we had our timer mechanism working, we decided to couple it to our storage for the density and the buoyancy like liquids. And so the way this works is that on the bottom compartment, you have the dense water. And so this threads in. So yeah, when Kimberly was saying we chopped this up and moved parts around, this part that normally adapts to the faucet was on this side. So we just moved it to this side so that we could work with it in the opposite direction. And so if this is filled with salt water or dense water, and this whole thing is coupled, only when the timer turns off is this able to go through. And separately at the top, we have a store for the oil to be stored in. And it can be like pushed in here and then plugged from the top, and it's able to keep the oil in. And so entirely, that means that because both sides are unpluggable, this is reusable. And because it's, well, currently it's made out of PLA, we obviously would not use that in the actual ocean, given that microplastics, we don't want to be littering that around. But we would still choose, of course, a lightweight but durable material. And also we just took very simple design precautions, such as like filleting some of the edges so that water does not shear the edges and then cause like even more plastic to fall off. So simple things.
Okay, so here, yeah, this is a slide of all the parts that we end up using. The exciting piece was like mainly we only used like our $10 hose timer, which we chopped up a lot.
One syringe. And then
the-
some like PLA, which
some
I think
PLA.
according to Purell cost estimates was probably like $2 or $3 worth. So yeah, under
Something
$15,
under
I
15.
think.
And this is an exciting part.
This is a video of us going from, I think the mechanism, we turned it on, so water should be flowing out, to turning it off. So.
On. Off.
So minimally leaky, but for the most
Yeah.
part, that was also before we had epoxied the O-ring. So I think now it might be a little more contained.
Yeah, so our next steps, this is where we're at right now, with the reverse hose timer. We also want to couple this with whatever we're using to sample our sediment. That way, like, we know the depth that it's going to start rising. We know the depth that it collects the sediment sample at. So we're thinking about using, like, this part naturally pops up for the timer itself. So if we could couple that with our sampler, then it would
So it
happen
would
at the
move
same
up
time.
and collect approximately like a 0.1 centimeter, like
Point.
1 centimeter cubed of sediment, I think.
Yeah. Yeah, because this rises up 1
Yeah.
centimeter. So that's our next piece that we want to work on, is the syringe part. In addition, we want to do some more calculations to, like, standardize the buoyancy and timing mechanisms. Like, as we said, we were kind of just playing around with the ping pong balls, but we could do some calculations there based on density and pressure to figure out what times and how much time we would need to sink to the bottom. In addition, as Troy was mentioning, thinking more about materials that we're using. And just more prototypes. This was just like one of our first ideas, so it can go many places from here. And yeah, so in the future, just like as an overall wrap up, these are all the areas. I mean, maybe we're missing an area, but mainly all the areas in the world that we have to explore. And there's so many species and so much biodiversity all around us. As the graph kind of represents, like, the deep sea is pretty much like the least known of there. So we're very excited for potentially something that can help us go explore and figure out what's there. So we want to go longitudinally, and we also, and also with the molecular basis, we can go down to a micro scale.
Yeah.
And
Thank you.
Let's do a quick round of Q&As, and we'll dive to the next theme. Comments, questions, threads, and of course, we'll do much more of deep dive threads in more discussion sessions. But how are we doing on time? I'm not doing that great on maybe 1 or 2 questions. Yeah, I mean, I think one thread to think a little bit about this would be is you have much of the mechanism working. It's really valuable to test it in experience
yeah,
and run the numbers. I think that will give you a sense of how large the 2 chambers need to be. Effectively, that sets the stage for, because there is a lot of passive weight that you can put. So going down is easy part.
yes,
The weight that going down is also easy. And to a certain extent, for retrieval, there is a certain minimum size you want the object to be. Because effectively spotting in high waves, spotting something is hard.
yeah,
The buoys are large for that reason, because the smaller the buoy, depending on the wave height, that's when you can spot them out.
yeah,
So there will be a critical size, back calculating that to then say, okay, this is the size object. Find the simplifies. Yeah, so I think it's time to do those numbers, because it will give you a sense of, and there's no in timer, there's no limit to what that time can be. And actually, we don't have to worry too much about how quickly it does the process.
Yeah.
It's useful to think about in retrieval, if within an hour or 2, if it would come back, then it's not too bad for the vessel that dropped it to actually pick it up.
yeah,
It would be, because if it's not the same vessel that picks that back up, then ocean currents on the surface will definitely carry it.
yeah,
Yeah, I think it's time to do some calculation.
totally.
But I mean that I think about some because the chamber is pre-sealed with water, right? it's exposing to another one, I don't know what are the time scale that it will take to completely replace the water. I think that's also another the diffusion time scale.
Yeah.
Definitely, because we were considering that with this, there's a very small hole in this device where water can flow out. You can see that it was dripping out very slowly. And so I think another next step would just be to, instead of using, now that we know how it works, like instead of using this device exactly, we would make our own main body that allows a larger dispersion rate.
I think Ray's saying something a little more subtle. What's happening is even if the faucet is completely open,
It just,
there's
yeah,
water on both sides. The only reason you would get them
Yeah.
is diffusion. And what you can do is take advantage of the fact that there was pressure. There is high
In-
pressure outside and low pressure inside. And what you want to do at that moment is use that to your advantage, but in the other way, so that there is an active system that might push that out.
yeah, we were thinking about that. And we're
Yeah.
considering that hopefully if we have enough oil or like pure water on one side, it would orient itself almost upright. So hopefully, because this material is more dense, we weren't sure if that would mean that it naturally would flow down and not just depend on diffusion.
The thing that comes to my mind is that, in my, here if the chamber of the water has two holes,
Mm,
it's kind of like,
Mm.
it's harder to replace the fluid when there's
yeah, that's true.
Yeah.
both and it's open. You are allowing active.
That's a good point. Yeah.
Yeah.
Yeah, I think it's, there are two ways. Either you can exploit the fact also that down below you are in a very high pressure. So, 4 kilometers, every 10 meters is an atmosphere. And so you have a gradient of pressure between the inside and the outside.
Mhm.
Unfortunately, that gradient is the opposite direction.
Yeah.
Right, and so there is high pressure outside, and what you want, but you can use that as a way to also move a piston, so you can get work done because
Mhm.
of that.
To get more to
Yeah.
push it out. Yeah.
I think it's, but the key is, the test would be valuable to actually do this test.
Yeah.
Add some dye, put a heavier solution. I think
Yeah.
now you have almost everything working. to
Yeah.
the Point
Yeah.
where even if it's slow, that doesn't matter so much. But
It'll still
get to a
go.
point. I think I tried doing that this week, so that at least there is one demonstration. If you were to put it in a long tube, it should go down. It
Yeah.
takes a certain time and it should come back.
Mhm.
Yeah.
Yeah.
We were gonna try to do it like on our side, like put it for 10 minutes during the presentation, but we didn't find that tube last night to, to put it in. Oh, perfect, perfect.
That's not too large.
Yeah.
And
Sweet.
Of course, the next thing is the swimming pool.
Yep, yep. Yeah.
Okay.
Cool.
let's see
Thank
the next
you.
meeting.